Hello, I'm David Baer. I'm a PhD student at the University of Innsbruck, and I will tell you something about an optimization problem Sebastian Stabinger, my supervisor Antonio Rodrigo Sanchez, and I detected. This optimization problem, called conflicting bundles, provably decreases the accuracy of neural networks. In this video, we also present a pruning algorithm to avoid this problem. I will describe the problem with the following example. Let's assume that our goal is to train a classifier to distinguish two different classes, the X and the O's shown in the right side of this slide. To classify those samples, we train a neural network with 3 hidden layers and a linear output layer. To classify those samples correctly, it's therefore necessary for each hidden layer to transform and compress samples in a way such that those samples are linear separable. So let's start with the transformation of the input when this mini-batch is propagated through the first hidden layer. We can see that the input data is transformed by this layer, and it's already a little bit easier to linear separate those classes. Let's continue with the second hidden layer. Now let's assume that the difference of some samples after applied to this layer is very small. More precisely, let's assume that the difference is less than the resolution provided by the floating point precision of GPUs or CPUs. We call those samples, shown in red, bundled. Here we can see 2 different bundles, one of size 2 and one of size 3. The bundles shown on this slide contain samples with different labels, and therefore we call them conflicting. The hidden layer 2 that created those bundles is called the conflicting layer. Let's now continue with the forward pass through hidden layer 3. Clearly, samples of the same bundle cannot be distinguished, and therefore they are still bundled after passing through this layer. The output layer cannot separate the bundled samples and misclassifies those. We show theoretically in our paper that also the gradient points into a misleading direction. Therefore, weight updates are not optimal and the accuracy of trained models is worsened. An empirical evaluation of this statement is shown on the next slide. In this slide we can see an accuracy map of 176 different fully connected neural networks trained on MNIST. Green parts of this image show a high accuracy, whereas white shows a low accuracy. It can be seen that deeper networks not always generalize better, and a good balance between width and depth is very important. The first layer that introduces conflicting bundles can be precisely detected already at the beginning of the training. We plot this boundary of the first layer as a red line in this graph. It can be seen that conflicting layers occur earlier in the network hierarchy as the width of the network decreases or the depth increases. Interestingly, we can also see that this boundary clearly separates models with high accuracy from models with low accuracy. Therefore, we conclude that conflicting bundles describe exactly this phenomena. We also evaluated convolutional neural networks and found a very similar behavior for this type of networks. We proved theoretically that residual connections bypass conflicting layers. But in our theoretical investigation, we also concluded the mapping of those layers is only linear from inputs to outputs. Therefore, we concluded that pruning of conflicting layers should have a very similar effect than the bypass of residual connections. We will show this on the next slide of this video. We called the algorithm that removes conflicting layers the autotune algorithm. As already mentioned, conflicting layers can be detected at the beginning of the training, and therefore this algorithm is computationally very cheap. In the table shown on this slide, we can see that the model found by this algorithm produces competitive accuracy when compared against the residual networks. But the model that is found by the autotune algorithm drastically reduces the memory consumption and the inference time, because all the conflicting layers are removed from the architecture. In this video, we introduce the conflicting bundles problem that decreases the accuracy of trained neural networks. We have shown that this problem depends on the depth and the width of neural networks. We propose the autotune algorithm to automatically adjust the architecture of networks in order to reduce the memory consumption and the inference time while preserving the accuracy. Thank you very much for watching this video.